Hello everybody, and welcome to the beginning of section 16.3. We're looking at page 65 of the workbook, and the topic of this section is triple integrals. We're going to build on some of the concepts that we did in the last two sections. And we'll start off this discussion with an example. Let's read this together. So let rho of x, y, and z give the density in grams per cubic centimeter of the solid prism shown on the right, and we'll assume that x, y, and z are all measured in centimeters. And it's our goal in this problem to find an expression for the mass of the prism. Okay, and before we dive into this, just a comment. If we knew that the density of this cube were constant, this would be a relatively easy problem because we could just take that constant density and multiply it by the volume. What makes it a more challenging problem is the fact that the density might change depending on where we're at in the cube. Okay, and so the strategy that we're going to use is similar to what we did in the previous few sections, to chop this cube up into smaller pieces and to find the mass of those pieces one piece at a time. Okay, so to get started doing that, I'm going to define a set E. Okay, this notation might be new for some of you, so I'm going to write it and then we'll talk about it briefly here. Okay, all this means is it's the set of points in three-dimensional space where x is between A and B, y is between C and D, and z is between R and S. That's just a way of describing the same cube that we're looking at over here on the right. Okay, the next thing that we're going to do is to assume that these little subcubes, okay, these pieces that our region has been chopped into have a particular size. We'll let delta x, delta y, and delta z be the length, width, and the height of each subcube. Okay, so height, we'll make this width and the last one height. Okay, just a way of measuring the size of each of our cubes. Okay, and we'll get started with this process by asking, how could we approximate the mass of the entire region E? Just approximate it, not calculate it exactly. Well, one strategy would be to assume that these subcubes over here are small enough so that we can just go to a cube one at a time, pick a point in the cube and measure the density. Okay, I'll call that rho of xi, yj, zk. Think of that as the density just at one point in the cube, and then we'll multiply it by the volume, okay, which would just be delta x times delta y times delta z, length times width times height. Okay, let's do a quick unit check here. Okay, so our density is measured in grams per cubic centimeter in this problem. Okay, and then if we take centimeters times centimeters times centimeters, we're going to get volume in centimeters cubed. Cancel your units and you can see that we're going to get grams, which is a unit of mass. Okay, so far what we have is an approximation of the mass of one of our subcubes. So to get an approximation for the mass of all of E, we would have to add up all of these cubes. Imagine going through that entire region E and going down every row and column, etc., until you've visited every cube. That's going to give you an idea of the mass of the entire solid. Okay, now why is this just an approximation and not an exact mass? Okay, well, you can think of it this way maybe. The density is changing. Even if you pick a point in one of these small cubes, the density is going to depend on where that point is. It's going to change a little bit depending on where you are in the subcube. Okay, so this is not exact, but we can make it closer to being exact by shrinking the size of our subcubes. In other words, letting delta x, delta y, and delta z get smaller. And if we take the limit as delta x, delta y, and delta z all go to 0, we're going to get the exact mass. Okay, so let's put that into words. Okay, taking this limit, we get the exact mass, and we can write that as follows. Okay, when we do that, this sum that we had up here is going to turn into an integral, and it's a special type of an integral called a triple integral. Here's the notation for it. It'll be the integral over the region E of the density function rho of x, y, z times dv. Okay, you can think of dv as just being a really small cube that you get after you've shrunk the dimensions all to 0. Okay, and you heard me say this in words, but I'm going to write it as well. This is called a triple integral. Okay, so this is kind of the three-dimensional analog of what we did back in sections 16.1 and 16.2. We're integrating. The difference is that we're integrating over 3 dimensions. Instead of integrating over a 2-dimensional area, we integrated over a 3-dimensional area. Okay, one last comment on this example. Okay, to calculate such an integral, we can use iterated integration. Okay, so in particular, we could take this triple integral and just integrate in the x, y, and the z direction separately. Okay, rho of x, y, z, and I'm just going to pick an order, dx, dy, dz, and then it would be a matter of writing down our limits of integration. Okay, we can look back at the beginning of the problem and sneak a peek here and see that our x's go from a to b, our y's go from c to d, and our z's go from r to s. Okay, if we put those on our limits, here's what we're going to get. Okay, and the rest of this section will be devoted to setting up and evaluating integrals like this.